In this lesson, we are going to conclude our investigation into Maxwell's contribution to electromagnetic theory, unifying electricity and magnetism into one theory. We certainly are not covered it in the detail that it deserves, and this would be the starting point for an introductory course in electrodynamics. But we have our complete list of Maxwell's equations in integral form, so you can write down here Gauss, Faraday, and Ampere-Maxwell. So we have studied these in detail throughout the course of the year, and hopefully we are comfortable now with those equations staring at us. So this page of notes is really about investigating a fascinating result we get when we look at these two constants together, the product of mu naught, epsilon naught. So epsilon naught we are going to look at first. That is our permittivity constant. I'm going to use Coulomb's as I show here. I'm using Coulomb's law to get the base units for epsilon naught. What I have done is solved for epsilon naught, put it on one side of the equation. F is in newtons, Q, Coulomb squared, R squared, meter squared. So, boom, we have epsilon naught in base units. Now, for the mu naught permissivity constant, I have to use two equations. So I used F equals QV cross B, our force equation. I solved it for B. F in newtons, Q in coulombs, V in meters per second. So I have that expression now to substitute in here in terms of its units. And Ampere's law then. So I take Ampere's law, solve it for mu naught. My green boxed equation here is my green boxed equation here. So that's the B. ds is meters, and I is coulombs per second. And I have my mu naught in base units, and I'm coming over here. I plug in my mu naught here. I plug in my epsilon naught here. And what we get is that mu naught times epsilon naught boils down to 1 over meters per second quantity squared. We know meters per second is V, so we get mu naught epsilon naught 1 on V squared. I bring the V squared up, the 1 on mu naught down. I plug in my units for mu naught now and epsilon, the values for mu naught and epsilon naught, not the units. And we get, as it shows here, boom, 3 times 10 to the 8 meters per second, the speed of light. So that was a number that caught Maxwell's attention. He knew that he was onto something. So please pause the video, as I said, and get this into your notes, and let's see what he was onto. So let's do it. What he was onto was ultimately the discovery of electromagnetic waves, and I have here Eureka. Now, part of this we have to just kind of take for granted because we have not studied the fundamental mathematical form for a wave, so you will have to take my word for it that this differential equation describes the propagation, the movement of a wave, a quantity in space based on wave motion, where 1 on V squared is the speed of the wave traveling. So this is the basic mathematical structure for any traveling wave. What Maxwell did, the brilliance of Maxwell, was that he was able to take those 4 equations and mathematically derive, show that the electric field and the magnetic field behaved according to these equations. So he, of course, understood the mathematics of waves. As we now have the 2 mathematical equations, we can compare them. They are the same mathematical structure. So we again have 1 on V squared equals mu naught epsilon naught, the speed of light. But now the waves are not just any waves. It's an electric and magnetic field wave, there is only one thing that travels at the speed of light, and that is light. So Maxwell determined the fundamental nature of light was comprised of electric and magnetic fields traveling together. He discovered this in the 1870s. It is amazing. It is still amazing today. And it ushered in the electromagnetic age and was part of the fabric of modern science. So absolutely amazing. So hopefully you've enjoyed our introduction to Maxwell's equations, and if you have the opportunity to continue on in physics and math, there is even more to learn.